So once you import your SolidWorks model into your SASCCM, you should able to visualize your geometries. So to visualize this, in fact, you just go to here, and click geometries, and it will show out. So you can zoom in and zoom out. So here you have the assemblies. You have a different component here. So if you click on it, you have the chimney, you have the collectors, and then you have the turbine. So you expand out your chimney, you have a different body inside. Now this chimney, it will be just one whole chimney. Remember that we create two cylinders, and because of this, now we have two of these surfaces. These surfaces will not serve purpose, in fact, for your simulations, because it is in fact just one whole chimney, and we can remove this. So we have the remaining surfaces, and if you wish to simplify it, in fact, we can move this folder and place it inside chimney. You can rename this one as a body. So what we can do at this point is we have to define the boundaries. So these faces represent faces of the entire chimney. So what we can do is we can split it. If we split by patch, we are able to see this chimney made out of different surfaces. This will be the outlet. So you can select this. Select this and select this, both of it, and name it as outlet. These are the chimney wall. You can select it as well. Both of this. And name it as chimney. Lastly, if we zoom in, we have this. This represents the interface between your rotating turbine regions and your chimney, and the bottom of the chimney. So you can say this is the interface, and the remaining you can name it this one as the surface. Now we will do the same to your collectors. So this is your collectors. So the collectors is made out of different faces as well, which you can split it. So this is the interface between your collectors and the rotating turbine. You can name it as an interface. This is the ground. This is the inlet. So there are two parts. This is the cover. Is the collector itself. Now the remaining are either the cover or the solar chimney, and the rest are, and you have the turbine base, and you can name it base. Okay, so in fact you can combine these two and your collector surface. This you can combine it and call it collectors. Alright, so that's your collectors. Now we move on to turbine. So this is so this is the interface between your turbine domain and your collectors. Right. So the top part between is the interface between your chimney and your turbine domain. You have these two. This you can name it as a wall. So the remaining really are the blades and also the body of the blades, which you can just collectively name it as blades. You can't do that, and you can name it here. So that's how you define, you providing your naming or your boundaries. Right, so the next step is create new regions. So we will have regions for the collectors and regions for the chimneys, and they are not moving. So you can rename this one as chimney. As collectors, as turbine, and we can simplify it by actually remove it from the groupings. So we can simply just delete this. Now it's much simpler, and we should be able to recognize a different part here. So we will define, we're putting the collectors and chimney together and name it as fluids. We create new regions for a turbine. Name this one as rotating. right? So now we create a new physics continents. So this is basically defining the boundary, the Gaussian equation that to solve uh, the solutions. So this will be a three-dimensional problems. We can have a gas inside. So it's implicit unsteady. We can use segregated couple. So we can use constant density with boosiness. You have to select we can use the fluid temperature model, use turbulent model, and use K epsilons. So this all you need in order to set your problems, and you can name this one as gas. And you need to double check your gravity, make sure your gravity will be along y directions. So put here your gravity. So you have to also set your reference temperature correctly. So this will be the temperatures of this will be the ambient temperatures, and you can set this one to be 300. So you have initial temperature 300 as well. So having defined all those, we can move on to defining the boundary conditions. So now we need to define the boundary conditions. So the default is wall. So in your fluid domains, what will be wall? You can name this one your chimney wall. Okay. And selecting your chimney wall. Create new. This is your collectors. So you can select collectors. Collector will be wall as well. And these two bits, we're gonna have they're acting like a wall, right? With adiabatic thermal specifications. So we're assuming there is no heat transfer through the wall, all right? Through the wall, both collectors and the chimney. Now move on to other boundary conditions, your outlets. So this is the pressure outlets. We define inlet using the pressure inlet as well. So your ground will be a wall as well, your ground. Because the ground absorbs heat, and you need to include actually a heat flux for your ground, and it would have a value of 300. Now we still have remaining boundary conditions that we need to specify. So we need to specify also the the base. The base will be wall as well. So we can assume that this is the base, and select your base, and it is diabetic as well. It's not absorbing any heat. Now the remaining bits are the interface. All right, the interface. So to differentiate between your chimney interface and your collector interface, we can name this one as interface followed by the name of the component. So you create a new wall and select the interface. For chimney, interface for collectors. Now we still have one, which is the inner surface, and it is a wall as well. Your inner surface. This is the inner surface of the solar chimney. So we got so we fully define the boundary condition for your fluids. Now we need to define for your rotating zone. Okay. So right. So we got the interface with chimney. We got interface for the collectors. Chimney, we have to select collectors, we have to select this. Obviously, there is a side wall. These are the side wall. They rotate together with the turbines. So we might consider this one actually to be a symmetry plan because it rotates together with the turbine. Now our blade, finally the blade itself will rotate, and it is a wall. At this point, we need to connect actually the interface between the fluids and the rotating zones. So for chimney and chimney, we can select both, right click and create an interface. And this interface will create a connections between your rotating zone and your fluid zones. So you do the same for the collectors, right click both of them and click create an interface. Okay, so this basically we fully define the boundary conditions. Right. So the pressure inlet, we need to check what's the temperatures. So this will be 300 will be the temperature of the fluid entering into the outlets. Now the zone is rotating, which means that we need to prescribe configurations that allow the zone to rotate. So we can go to tool here, go to motions, right click, and select our rotations. So over here we can select actually we can specify the rotation rate of these turbines. Say it is rotating at 100 RPM. Okay. Now we need to define the reference frame for your rotations. So here we define the axis of the rotations. So clearly it is rotating about y, so we can place here as 1. Okay. So here, this is where we define the rotations. So you place this one 1. This you're assigning the domain to rotate around y-axis, and you're defining the axis of the origins. Okay, this one you can define this one to be 10 because your turbine domain is resting around at a height of 10. Okay, so if you, after you define this one, you can assign right now. You can assign your rotating motion specification here to be rotations, right? So this will link, this will assign your rotations according to the specifications that you include in your tools section here. Okay, so we fully define our boundary conditions, we fully define our Gaussian equations. So the next step is to next step will be creating the mesh. So the meshings, how we can create a mesh, we can go to operations, click new, automated. So we can choose here, say we wish to we can mesh this part by part, which means that we will mesh chimney first using the meshes. So there are three types of mesh you can use: polyhedral, tetrahedral, and trim cell. So trim cell possibly would be a very good option here because we're trying to use as least amount of mesh as possible at this point. Now this is prism layer, is the option to create boundary layers. So click OK. Here we can specify what will be the base size. Okay. So at the first start, we do not want to have so many cells. So it will be a good idea to use a big base size in order to reduce the cell count, the mesh count. So I thought we can use this one as 10. Obviously, you need to include prism layers. So this is the boundary layers. We can include 10. So this automated mesh will mesh your chimneys. However, we need to take note that very close to this rotating zone, we got very small components. So it is likely that we will mesh your rotating zones here with small mesh, with tiny mesh. So this means that close to this surface, we're expecting actually to have more mesh, more tiny mesh on this surface. So what we can do is we can create a custom control, surface control here. Okay, and basically select your interface, inner surface and interface. So we're selecting this surface. And assign custom values. So this could be something smaller than your base size. So it could be 1% with 5% of what your what will be the target base size of your mesh inside your chimneys. Now this is the interface. You can disable it as well, disable the boundary layers in fact on this surface. So you can execute. So executing this the solver will generate the mesh in the domains. So we can now we can visualize the mesh. We can go to mesh, and this here it will shows show you the mesh, what it looks like. So we have assigned a very coarse mesh. Okay, so this is what it looks like, and we can see some mesh distributions, more mesh distributions close to the boundary. So these are the boundary layers. Okay. And over here, close to the interface, we can see a mesh, a tinier mesh as well. Okay, due to the here, because we are assigned here to have a smaller mesh size. So here is not very ideal. In fact, we can try to optimize here to perhaps reduce the number of prism layers to just 5 and see what the result looks like. This is probably too coarse. Again, this is probably too coarse. We definitely need 2%. Ideally, the prism layer that is not too thick as well. So this represents the prism layers. And we can reduce this one. So now we achieve better. This will be the mesh distributions at the interface. And this is what it looks like from the top. So for the top, we have less mesh, and we prescribe more mesh. Here, due to it being connected, being connected with your rotating zones. So you can name this one as your chimney and create a second mesh operations for your turbine. Rename this one as your turbine. So this is the regions. This is the regions, rotating zones, and this is the crucial regions, and we will need small base size to capture actually to create more mesh surround your turbine blades. You can specify the prism layer. So we probably need also more mesh close to your turbines. It's a good idea actually for your blades. We prescribed um, more mesh on the surface of the blades so that we can capture the flow around the blades. So what we can do is we can reduce the percentage of the base, say it's 10%. Okay. Now, we can remove also the boundary layers, the interface, the prism layer, the interface, and we can create a separate surface control. This would be for the interface, and now we set that there's no prism layers. So say we mesh this and see what it looks like. So that has taken a while is because there are more mesh, in fact, in the turbine region. So now we can see how actually it looks like. Okay. Because of the surface control that we prescribed, we can see more mesh actually at the blade there. Okay. Now, if we wish to see how it looks like in the middle, another possibility is we can define a plane, a new plane. Define a plane. Define it at tempo 2 perhaps. You can name this one as turbine. So we cut to the turbine. And define your mesh. Should be based on that turbine cuts, right? Now we can use the standard view. Okay. So this is what the meshing looks like, cutting through the turbine domain. We can adjust this one, input 1. Input 1 file. So input 1 file, in fact, you can see how the mesh distributes around your turbines in more detail. Okay, so this is the mesh, how to generate mesh, more mesh surround your turbine blades. So lastly, we can create meshing operations for your collectors. So we're going to use the same trim cell with prism layer as well. So this will be the meshings in the final part, your collectors. So so it's a big collectors. We can use large size as a sort. We can try with 20 and perhaps put 5 prism layers and see what it looks like. Now we need again to consider a surface control, create a surface control for the interface. So the interface there, we know that we're going to need tinier mesh, and we can prescribe this one to be it was 2%, right? So 5%. And this one is the collectors. And execute and see what result that we can get. So this is what the mesh looks like in overall. And we can actually create another plan, to visualize the inner sections of your mesh. So we can go to derive part here again and create a new plan. Create a new sections. So this is cut through the body, right? You can So we could try to visualize, create another meshing scene, new meshing scene, and that is based on our new derived part. So disable this. So this would be what the meshing looks like inside the models. So there's a possibility, in fact, we can include more layers, prism layers inside our collectors, and we could go to and perhaps increase this one to 40 and increase more layers, maybe 7, and see what it looks like. So these are the final results. And now we are actually ready to um, run the simulations. So a few things uh, that we should consider before running the solver itself. Um, this will be the time step needed. How many iterations per time steps? When is the simulation stopping? 1 second? The maximum amount of steps. Okay, we need to possibly monitor a few parameters while we're running the simulations. So this report function is very good. say, to get the surface area of some parameters. So this could be the mass flow rate, at the outlet, so this will output what will be the average flow rate that is leaving through the outlet boundaries. We can use this one, in fact, is to get the mesh count of your regions, right? We can run this one report and we get some idea how many cell counts are being used in each regions, right, in your model. Pressure drops between the interface. So it would be the inlet will be the collectors. Chimney will be the outlet, lower pressures. So there is a pressure drop through the turbine, and we can compute that one as well. We can do the moment force. Okay, and look at the force. Way to define the axis. This will be the force on your turbine. Boundary one. So this could be the force on your turbine. So we can monitor that one as well. We can actually create and monitor the plots from these moments, okay, and as it runs, as the simulation progresses, we can see how the moment actually changes, right? Now, of course, we can create the velocity contour, the vector contour, the kind of things. Then we can go to the scene here. Say we're interested to look at the velocity, velocity contour. We can go to a scalar. Here and choose, so we wish to see actually how the velocity changes as the turbine rotates. So we can choose that, choose the velocity. At the turbine card. Can even rename this one as velocity. Okay. Now, now we got many things already. We're almost ready to simulate. So we can the residual, right? Can open it, and this allow us to track uh, how the solution is progressing through the iterations. Okay. So to simulate this, we initialize the solutions, right? And we run. As you can see, the rotations at the very first time steps. Now we might need, in fact, more iteration per time steps in order to avoid the solution being blown out. So we can increase the iterations to 20. So we can observe here, this is the residual of each governing equations for continuity, momentums, and energy equations, as well as the turbulent equations. So right here we have the graphical representative of this residual as a function of iterations. Now we increase the iteration to 20. And these simulations, in fact, will take more iterations before they progress to the next time step. So you can see the turbine turn at each time steps. So how much it turns depends on the time step that we prescribed. So we prescribe a time step here in implicit unsteady. So we prescribe to be 0.01. So there are two factors here. It could be the rotations. Remember, we set the rotations in our two sections. So if we set the rotation to be too large, the smaller time step that we need in order to capture the rotations of the turbines. Okay, so we should not use too large time steps, otherwise the motion will become too big. The solution will be harder to converge, and we are not able to capture actually the physics around the turbine blades. So here we can see the moment also. So the moment here will change as we as the solutions actually becoming the residue reduces with as the time step progress. Okay, as the time step progress, we will see lesser residual, and we can see also lesser change eventually in a moment. Right. So in this video, we successfully cover all the important steps in order to set up a CAD simulation to simulate uh, your solar lighting power plant. So we cover the boundary conditions, doing the meshings, and also setting the appropriate parameters to close your result. Right? So thank you, and good luck in your simulations.